Hello everyone, and welcome to today's chem lesson. Today, we're going to look at the different types of reactions. Right? We've looked at balancing reactions, we've looked at what we can do once a reaction is balanced, but something we never looked at is the different patterns, the different types of reactions that exist. There are 5 different types of reactions that we are going to look at, and each one comes with a pattern that we're going to try our best to easily recognize as we look at any reaction. These 5 reaction types, synthesis or combination, right, same name for this type of reaction, is when there's multiple reactants coming together to form one product. Decomposition is one reactant breaking down into multiple products. Single replacement involves an element by itself taking the spot of an element that is in a compound. A double replacement involves 2 elements swapping partners in 2 different compounds. And a combustion is the reaction of a hydrocarbon with oxygen to make water and carbon dioxide. Now we're going to look at each one of these in more detail. I'm going to write those definitions down for us. So let's take a look at our 5 reaction types and their patterns. Let's spread them out a little. A synthesis or combination reaction is any time multiple reactants make one product. And we know from our experience that reactants are the things on the left, and products are the things on the right. So anytime you see multiple reactants coming together to make just one product, you know you have a synthesis or combination reaction. Now that can be multiple things, right? It doesn't need to be just 2, it could be 3 or 4 coming together to form a compound. It could be 2 compounds coming together to make a bigger compound. It could be elements and a compound coming together to make a bigger compound. Right? Anytime there's multiple reactants coming together to form one product, you have a synthesis reaction. Now, a decomposition is the exact opposite. A decomposition is any time there's one reactant breaking down to form multiple products. And again, we get the same kind of open-endedness to it. Right, one reactant, multiple products. Decomposition can look like this: one big compound breaking down into elements. It could be one compound breaking down into smaller compounds. It could be one big compound breaking apart into some combination of elements and compounds. But as long as there is one reactant and multiple products, you have a decomposition reaction. These are the 2 easiest types of reactions to identify because you can just look at the numbers of reactants and products and know immediately if you have decomposition or synthesis. Single replacement is a little bit trickier. We can't just look at the pattern, we have to also look at what's going on inside the reaction. And like I said before, you're going to get an element replacing a different element in a compound. Right? A lone element replaces part of a compound. Now this happens pretty often. Right here, in this case, the aluminum replaces the hydrogen, and the aluminum comes in to kick out the hydrogen from its spot. A double replacement is a swap. Two elements trade spots. Right? Instead of one element coming to replace, right, like a single replacement, one element comes and kicks the other one out of a compound. In a double replacement, here we're going to watch the M and the G are going to trade spots with each other. So F was with G, now F is with M. L was with M, now L is with G. So the M replaced the G replaced the M. Right, this is another thing that we can see with ionic bonding. Here, in this case, the sodium and the silver swapped places. It was silver with the chlorine, now it's sodium with the chlorine. It was sodium with the iodine, now it's silver with the iodine. Right, there were two swaps. There's a trade that occurs here. Combustion, our last one, is much more specific. Here, right, I use just random letters to kind of show the patterns of these things, but for combustion, I'm actually using elements. Right? Combustion is when a hydrocarbon reacts with oxygen to make CO2 and water. You will always have CO2 and water as your products in a combustion. If there's something else, then it's not a combustion anymore. Right? Combustion by default is hydrocarbon and oxygen making water and carbon dioxide. Let's try to practice this a little. Let's take a look at these three reactions and see if you can correctly identify what each of them are. There are three different questions here, right? Reaction A is synthesis, decomposition, single replacement, or double replacement. Reaction B is synthesis, decomposition, single replacement, double replacement. Reaction C is synthesis, decomposition, single replacement, double replacement. Right, so three different answers, one for A, one for B, one for C. When we look at these, we have a decomposition, followed by a single replacement, followed by a synthesis. We know that A is a decomposition. It's one reactant that becomes two products. We know that C is a synthesis. It's two reactants that become one product. When we look at B, we can see it's a single replacement because the zinc replaces the hydrogen. Hydrogen was with the chlorine, now zinc is with the chlorine. There was one replacement that happened there. And now we need to ask ourselves a little bit more about single replacement. If this is a reaction that happens can the opposite happen? This is also a single replacement. But can they both be possible? If zinc replaces hydrogen, can hydrogen replace zinc? The answer to that question is no. Only one of these things can happen. And we can tell which one is going to happen by looking over at Table J. Table J is the activity series, and it tells us how strong our elements are, and how good they are at replacing each other. The higher up on Table J an element is, the better it is at replacing. The worse it is at being replaced. This acts as a totem pole, a list of strength, with lithium at the top. Lithium is the strongest, gold at the bottom. Gold is the weakest. An element can replace any elements that are below it. So when I look at an example, this reaction will happen. Potassium is higher on the table than nickel is. So this reaction happens. But if I try to reverse it, this reaction does not happen. Nickel can only replace things that are lower than it, and potassium is much higher. That means that we could look at any single replacement reaction, any reaction that we want, and say if it will happen or not based on Table J. Right now, this is only for single replacements. It will come back again later in a different unit, but we're not there today. Right now, we're looking at single replacements and seeing if they will go forward or not. Right? The higher element gets to be in the compound. And if it is already in the compound, the reaction will not happen. Let's try one more example here before we jump into some practice problems. All right, copper and aluminum. One of these reactions will happen, the other one will not. Can you tell which reaction will happen and which one will not? if we look at these two elements, right, we've got copper and aluminum, only one of these reactions will go forward. The bottom reaction is the one that will happen, the top one will not. Copper is not strong enough to replace aluminum. Aluminum is stronger. Aluminum will replace copper, so this will happen and we will get the other half of the reaction with aluminum in the compound and copper by itself. But this will not happen because copper is lower down. The higher element is the one that gets to be in the compound. If it's already in the compound, then there's no reaction that's going to happen. Let's look at some examples here. Will this reaction happen? This reaction will happen. If we look at our two elements, we've got zinc and hydrogen. Zinc is higher than hydrogen. Zinc is able to replace hydrogen. So this will happen, and we will get the other half of the reaction, which would say H2 and ZnCl2. Zinc is stronger. Zinc is higher up on the table than hydrogen is, and so zinc will replace hydrogen. What about this one? Copper and HCl, copper and hydrochloric acid. This reaction will not happen. If we look at our two elements, hydrogen is higher than copper. Hydrogen can replace copper, but copper cannot replace hydrogen, so this reaction has no other half. When you mix these two things together, nothing happens. One more for good measure. Will this reaction happen? This reaction will not happen. If we look at our two elements, zinc is higher than iron. Zinc can replace iron. Iron cannot replace zinc, so this reaction does not proceed. Table J comes back in a big way when we start talking about electrochem and looking at oxidation and reduction. But like I said before, that is not a conversation that we're going to have right now. We're not up to that uni yet, so we're going to put that on hold until later. For now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.